Hello, hi. Um, okay, so my name is Niket, and I'm going to be taking these live sessions for the course Mathematical Methods in Physics, part two. All right, so okay, you're welcome. Um, okay, I'm assuming that you guys have seen the lectures and maybe tried the assignment, or even if you haven't, actually, the last year's assignment and this year's assignment is the same. So what I'll be doing is I am at least putting up the questions of the assignment itself, but I'll not be solving them completely because it's actually your job to solve them. But what I'm going to do is show you some direction. So, for example, this first question right here. So, I'll not be solving all the parts. Okay. It requires you to mark all the correct statements. If you can read the question, which of the following must hold for an arbitrary complex number z? Mark all true statements. So, if I take an example of this question, I will not be solving all the parts. I will give you a flavor and idea as to how you can solve this particular kind of question, and the remaining parts you can solve yourself, right? Okay, so this is the way we are proceeding, and please, yeah, so keep the interaction live, keep on asking doubts in between, and like you can unmute because it's just two people, so you can unmute your mics and let's have a discussion, okay? Let me not be giving a wholesome lecture or something. Let's have a discussion. So it would be nice if both of you can unmute and just keep on talking whenever you want, all right? Okay, so let's start with the first one. So this is assignment one, question one. The question is, which of the following must hold for an arbitrary complex number z? Mark all the statements which are true. Okay, so here a few statements you might yourself know which might be false or true. I am going to start with the first one, this one, square root 2 mod z is greater than or equal to mod real part of z plus modulus of mod imaginary part of z. So I'm going to try and prove this inequality. All right. The rest you can prove yourself. Okay. So for this inequality, let's look at the left hand side. So z is normally real part of z plus imaginary part of z, of course. This is my z. So if I want to write mod z is equal to square root of real part of z the whole square plus imaginary part of z the whole square. Sorry, here there will be an I as well. Right. So this is what we get, right? And if I'm saying square root of 2 mod z, so that is equal to square root of 2 into this, 2 into real part of z the whole square plus 2 into imaginary part of z the whole square. Okay, so this is my left hand side. Let's see the right hand side. Okay, so maybe what I can do is I can square the left hand side, which makes it 2 mod z square is equal to simply 2 real part of z the whole square plus 2 into imaginary part of z the whole square. All right, now for the right hand side, I am squaring the right hand side as well. See, these are positive numbers on both sides. So squaring won't change the inequality. If there was a negative number on one side, the inequality can be reversed upon squaring. So we have to be careful there. But here there is no such problem. So I can directly do that, right? So upon squaring the right hand side, what I get is real z plus imaginary z the whole square is equal to real z square. So let's keep mod here, but after squaring does not really matter. The mod goes away plus imaginary part of z the whole square plus 2 real part of z into imaginary part of z. That's what I end up getting. Here mod will matter, so I keep a modulus here. Okay, so what we want to prove is that equation 1 is greater than equation 2, greater than or equal to. So let's try and see that 2 real of z square plus 2 imaginary z square is greater than or equal to real z square plus imaginary z square. plus 2 real z imaginary z. Okay, so this is the inequality that we have. I have just written it as in the form of an inequality, but we have to prove this. So how do I prove this? Uh, Let me just cancel out these. So what I'm left with is real z the whole square plus imaginary z the whole square is greater than or equal to 2 into, I'll take this 2 in the denominator on the left hand side, divided by 2 is greater than or equal to real z mod into imaginary z mod. This is what I have. Is this something that you have seen somewhere else, anywhere? Can you recognize this structure and tell me whether this inequality holds true or not for all cases? So we are talking about a very general complex number. So anyone? Can't hear you. Can you repeat what you said? Okay, so consider two numbers A. Sorry, come again. Actually, your voice is not very clear. So, okay, anyway, I'll say. So basically, suppose a real part of Z and imaginary part of Z. These are two real numbers. Okay, let me call A as real part of Z and B as imaginary part of Z. And of course, A and B both are real numbers because imaginary part of Z is also a real number with an I outside. So A and B both are real numbers. So we know that this, sorry, A is real part of Z square and B is imaginary part of Z square. Okay, not just the real and imaginary part. Okay, so now what I'm saying is that we generally know that arithmetic mean is greater than or equal to geometric mean. The arithmetic mean in this case is a plus b by 2, and we know that this is always greater than or equal to square root of ab, right? So that's what is the inequality here being applicable. A plus b by 2 is the left hand side. If I am solving this out, real part of z the whole square plus imaginary part of z the whole square divided by 2 is greater than or equal to square root of real part of z square into imaginary part of z square. If I take the square root, this is what I end up getting, right? So basically what I proved is that this particular inequality here, which I'm marking with an arrow, this inequality holds true for any complex number z. Hence, the statement that we started with, that square root of z is greater than or equal to this square root 2 mod z greater than or equal to real part of z mod plus imaginary part of z mod. This statement holds true for all z. Is that convincing? Is that okay? Which means that this statement is true. Statement 1 is true. That is what we proved. Now remaining three statements is something that you can prove. It's not very difficult. You can see that they are fairly straightforward. So you can go ahead and prove those. Is that okay for everyone? All right. Okay, so that was the first question. Now we have the second one. The second one says that consider any three arbitrary complex numbers z1, z2, z3, and they're asking which of the following given statements are true. You have to again mark all the correct answers. In the first question also, you have to mark all the correct ones. Even this one, you have to mark all the correct ones. So here there are four questions, four parts. First part is obviously directly the triangle inequality. Second part, um, second part, third part, fourth part are something you have to do a little bit of manipulation. So what I'll be doing is I'll solve only the third part here. Uh, Second and fourth part you can look by yourself, following the method of the third part. So it should be fairly straightforward after that. Okay. Okay. So let's do this. Uh, what I want to prove is that mod z1 plus Z2 plus Z3 is greater than or equal to mod Z1 minus mod Z2 minus mod Z3. This is what I want to prove. By the way, I don't want to prove this. I want to check whether this statement is true or not. Okay, so I don't know whether it's true or not. So that's what I want to prove. Okay, so let me define a complex number Z, which is just Z1. Okay, and I'll define another complex number Z prime, which is Z2 plus Z3. Okay, so using triangle inequality on these two complex numbers, what I get is mod Z plus Z prime, mod of Z plus Z prime is less than or sorry is greater than or equal to mod Z minus mod Z prime, the second form, the second part, right? Mod Z plus mod Z prime is greater than or equal to mod of Z plus Z prime is greater than or equal to mod Z minus mod Z prime. Is this okay? So I am basically using only this much of the inequality. So substituting the values I have used, the left hand side is mod Z1 plus Z2 plus Z3 is greater than or equal to mod Z1 minus mod of Z2 plus Z3. Okay. So now, if I want to further break this, I know that mod Z2 plus Z3 is greater than or equal to mod Z2 minus mod Z3. Again, using triangle inequality on this one as well. I know this, but putting it here, what I get is mod Z1 minus mod Z2 plus mod Z3 is not the form I want. This is not the form I want, right? I want both negative. So I would have to use the left hand side of it, mod Z2 plus mod Z3. This is what I need to use, this part. But the problem is that mod Z2 plus mod Z3 can be greater than or equal to mod of Z2 plus Z3, right? So whether substituting this left hand side here in this part, I am not sure whether the inequality that I have started with, that is this being greater than or equal to Z1 minus this, will still satisfy, right? I'll repeat my statement. So what I'm saying is that I have already established that this is true. Z1 plus Z2 plus Z3 mod is greater than or equal to mod Z1 minus mod of Z2 plus Z3. This I have already established. But if I want to break this further, on the right hand side where I am manipulating just the mod Z2 plus Z3 part, if I am able to establish that uh, if I'm able to establish that minus of Z2 plus Z3, this one is still smaller, further smaller, then the inequality will always hold. But what's happening is to bring this part, to bring minus mod Z2 minus mod Z3 on the right hand side, I will have to use the left hand part of the inequality, wherein mod of Z2 plus mod of Z3 can be greater than mod Z2 plus Z3. It's not necessarily equal, it's mostly greater, sometimes only it's equal when both are equal, right? Both are aligned. So if I'm using the left hand side part, I am not assured whether the previous inequality still holds, right? Is there a doubt? Is this clear? Please tell me. Okay, maybe I'll write it down mathematically. Let me do this. So what I'm saying is mod z1 minus mod of z2 plus z3 is actually less than or equal to mod z1 minus mod z2 minus mod z3. I'll of course have to take an overall mod here on both sides. But you get the idea, right? That this is actually less than or equal to this, not greater than, because when I'm breaking mod of z2 plus z3, okay, wait, sorry. Hmm. I actually can't hear you very clearly. Can you repeat? You are you are not at all audible. Your voice is breaking really bad. Do you have something to add here? Okay. Anyway, I'll continue. Okay. So what I was trying to say is that okay. Let me do this. Z2 plus Z3 is less than or equal to mod of Z2 plus mod Z3, right? This is established. So I have taken negative sign here. Mod Z2 plus Z3 is greater than or equal to minus of mod Z2 minus mod Z3. Is this okay? This, yeah, because since I'm taking a negative sign, the inequality gets reversed. Now I'm putting Z1 also on the left. So mod Z1, here also mod Z1. So what this establishes is that mod of Z1 minus Z2 plus Z3 will always be greater than this left right hand side, right? And this is the left hand side here. So basically this is always greater than or equal to mod Z1 minus mod Z2 minus mod Z3. This expression is always greater than or equal to mod Z1 minus mod Z2 minus mod Z3. So basically what we have established is this also will always be greater than this. Therefore, mod Z1 plus Z2 plus Z3 will have to be greater than or equal to mod Z1 minus mod Z2 minus mod Z3. So basically this expression is correct. That's the conclusion. Is that clear to everyone? Right? Please freely ask any doubts if you have. All I did was, the only trick that I used here was that I had to split the complex numbers. So there are three complex numbers. I'm splitting it in the set of twos and using triangle inequality more than once. So you should be able to establish whatever you want to prove. Similarly, for fourth question, if I just want to give a hint for the fourth part, this one, I'm talking about this part. For the fourth part, if I want to give some hint, you can take z, some z complex number as z1, and you can take another complex number as say 2z2 plus 3z3, something of that sort. So you'll be able to establish a very similar identity for that as well. In a very similar manner, you'll be able to do the fourth part also. And other parts you can check similarly. Is that fine? Is the second question okay? Okay, assume. Okay, Fine. So the third question is also very similar in lines. Um, let's see. For question number three, maybe I'll solve just these two parts, second and third part. Rest you can solve yourself. Or if you know these parts, maybe I can skip this also. Do you want me to solve any of the parts, or should I skip this? I need some answer. Should I skip this question? Should I do this question? Because it is kind of on a similar basis. That's why I'm asking. Okay, anyway, I can skip. Okay. Um, all right. So I'm not solving this one. Maybe I'll just nonetheless go ahead and show one part. Everything else you can. So probably this is some other variety, I think. So I'll just show you this one part quickly, and I'll skip the rest. Okay. So we're talking about this particular expression. So again, what I'll do is I'll take z is equal to z1 plus z2 plus z3, and z prime is equal to z4. So using the triangle inequality, modulus of z1 plus z2, basically it's modulus of z plus z prime is greater than or equal to modulus of z minus modulus of z prime. Therefore, z1 plus z2 plus z3 plus z4 modulus is greater than or equal to this modulus minus z prime. This is what I end up with. But what I want is even this has to be individual moduluses, not the entire expression. So let's do that. But the problem here is that this is less than or equal to mod z1 plus mod z2 plus mod z3. So this right hand side expression is what I want here. But the problem is that this right hand side expression is greater than mod of z1 plus z2 plus z3. So here if I put it this this right hand side quantity, this right hand side quantity can become greater than the left hand side also. If I put up mod z1 plus mod z2 plus mod z3 minus mod z4, I don't know whether this inequality still holds or the inequality gets reversed, because this quantity is greater than this quantity. Modulus of z1 plus mod z2 plus mod z3 is greater than modulus of z1 plus z2 plus z3. So whether the inequality still holds, whether this is still lesser than the left hand side, or it becomes greater, we don't know. So in this case, it is undecided. And in this case, you cannot say whether this is true for all arbitrary complex numbers. It can be true for some complex numbers, it can be untrue for other complex numbers. Do you get the idea? Is this clear? So this is what we get. If you can see this left hand side, mod of z1 plus z2 plus z3 plus z4 is greater than or equal to this expression, which is less than this expression. So I can't directly establish a link between this and this. I can't establish a direct link between the left hand side expression of the whole modulus and this right hand side expression. There is no direct link that I can establish. So that is why here I can't say for sure whether it's going to be greater or lesser. Okay. So this will remain undecided, and this statement is not always true for all arbitrary complex numbers. It can be untrue for some numbers. So that's why this statement is untrue. So we will not be marking this. So that is question 3. Is this clear? Okay. All right. So moving on to the next question, question 4. Explicitly check if the Cauchy-Riemann conditions hold for each of these functions and mark all the correct answers. Okay, so tell me something. What is the Cauchy-Riemann condition for f of z? Some function f of z. If I tell you, what is the Cauchy-Riemann condition for this? If you watch the lectures, please tell me what is this. Like there are Cauchy-Riemann conditions giving a relation between u and v, which are the real and imaginary components of any function, right? But when it's a function of pure z, then what is the Cauchy-Riemann condition? Okay, so the Cauchy-Riemann condition is del f by del z star has to be equal to 0. So z and z star are independent variables, and del f by del z star has to be 0. This is the alternate form of Cauchy-Riemann conditions. Is this okay? You know this, right? If not, refer to the lectures. Lectures, of course, mention this. So, okay, so say for example, f of z is equal to z square. I am looking at this second one. F of z is equal to z square. So here, del f by del z star is clearly equal to 0 because there is no z star here. So therefore, this satisfies. I'll write here satisfies. What about mod z square? So when fz is equal to mod z square, this is basically z into z star. So del f by del z star is equal to simply z, which is not equal to 0. Hence does not satisfy. Doesn't satisfy. This one I'll put as a tick mark maybe. It satisfies. Similarly, I'll pick up another function like this. For this case, f of z is equal to sine x. So here I am saying f is a function of x comma y actually, right? So here we'll use that those conditions. Well, this is more those conditions will be more applicable, where we said that del u by del x is equal to del v by del y, del u by del y is equal to negative of del v by del x. So these are the standard Cauchy-Riemann conditions that we have studied. So this is what we'll use here in this case. What is u? U is simply sine x, the real part. What is v, the imaginary part? 0. So using these conditions, del u by del x is equal to cos x, and del v by del y is equal to 0. So del u by del x is not equal to del v by del y. Therefore, not satisfied. So f of z is sine x does not satisfy Cauchy-Riemann conditions. Right. And similarly, you can check the others. You can check all the others here. There are many functions. Just go ahead and use these conditions and check and mark all the correct answers in the assignment. Is this okay? This is pretty straightforward, so I hope there's no confusion. Okay. The recording is going on, right? Yes. Okay. Now, what this question says is find the derivative of these functions. There are four functions given below. Find the derivative of these functions uh, using first principles. And they're asking which of the following statements are true. So we have to evaluate derivative of all the functions and check whether the statement that they've given is true or not. So in this case also, I'll solve the first two. The rest is your responsibility. So f1 of z is equal to 4z cube plus 3z square plus 1. So del f1 by del z is equal to f1 of z plus delta z minus f1 of z divided by delta z, where limit delta z tends to 0, right? So this is what I'll write: 4 into z plus del z the whole cube plus 3 into z plus del z the whole square plus 1 minus 4z cube minus 3z square minus 1 divided by del z. Here, because del z is tending to 0, it's very small. So of course I'll expand this each and every function here up till linear ordinary del z only. So this is equal to 4 into z cube plus 3z square delta z. And there are other terms which I'll ignore. The other terms I'll be ignoring here. Plus 3 into z square plus 2z delta z. And ignore the del z square term. Plus 1 minus 4z cube minus 3z square minus 1. So this cancels out. 3z square cancels out from here. 4z cube cancels out from here. What I end up getting, okay, there is a delta z also, the denominator, delta z. So what I end up getting is 12z square delta z plus 6z delta z divided by delta z. So this comes out to be 12z square plus 6z. This is your final answer. So here this option is also equal to 12z square plus 6z. So you know that this statement is correct. So that is what we established, that statement 1 is correct. Okay. Now moving on to f2 of z. F2 of z is equal to z plus 4 divided by z minus 4. Z plus 4 divided by z minus 4. And I have to take this derivative from first principles itself. Okay, so again del f2 z by dz is equal to limit delta z tending to 0, z plus delta z plus 4 divided by z plus delta z minus 4. So this is just f2 of z plus delta z, right? And here I have to write f2 of z. F2 of z is what I'll write here. So that is z plus 4 divided by z minus 4. And this whole divided by delta z, right? I hope you guys are following what I'm doing here. There are no questions, right? This is just first principle method that again has been shown in the lecture, and you also know you learn differentiation from first principles. You know how to do this, right? Any response, guys? Yes, no? Okay, fine. All right, sure. So, okay, what we can do here is simply cross multiply. So let's do that. Hmm, z plus del z plus 4 multiplied by z minus 4 minus of z plus 4 into z plus del z minus 4 divided by z plus del z minus 4 into z minus 4, the whole divided by del z. Okay, so what this gives me is z square plus z del z plus 4z minus 4z, 4z minus 4z minus 4 delta z minus 16. I hope I have not made any mistakes here. Z square, okay, minus 4z minus 4 delta z minus 16. Perfect. This looks okay. Minus of z square plus z delta z minus 4z um, plus 4z plus 4 delta z minus 16. This is the whole expression divided by delta z into the denominator would be uh, z square minus 8z plus 16 plus z delta z minus 4 delta z. Z minus 4 the whole square, which is this. Yes, yes, this should be the answer. Okay, so now let's evaluate this. So z square gets cancelled off. Z delta z also gets cancelled off. Um, 4z remains. So I have say 8z here. So minus becomes plus. Yeah. Oh, sorry. Here itself it gets cancelled away, and this also gets cancelled away. So no, there is no 8z. There is minus 8 delta z though. Minus 8 delta z and 16 also gets cancelled off. So the only thing that I have remaining in the numerator is minus 8 delta z. In the denominator there is delta z, and there is this whole term where this I ignore because this gets cancelled. But otherwise these delta z's are small, so I can let them go. I can ignore them. So what I'm left with is z square minus 8z plus 16, which is equal to minus 8 divided by z minus 4 the whole square. Here basically I took the limit that delta z is tending to 0. I can't take that in the first place, right? Because I have to cancel out terms. So I can't take it right in the beginning. But once everything else is solved, I can simply take delta z tends to 0 limit. So what I get here in the denominator is just simply z minus 4 the whole square. And in the numerator, I have minus 8. So let's see whether this matches. Minus of 8 upon z minus 4 the whole square. So this is correct, and even second one is correct. So both these options are correct. Option 1 and 2 both are correct. The other options you can just check similarly, right? Is there any doubt here? All right, perfect. So that is question number 5. Okay. Moving on to question 6. Mark all the functions f of z for which the derivative f prime of z exists at least one point. So we are not saying that the derivative should in general exist. We want the derivative to exist at least one point, any particular point. So here the method could be like there could be many methods to do this. One simple method could be you can simply use Cauchy-Riemann conditions itself and check where the conditions are being satisfied. Or you can use the very fundamental principle where you take the derivative by approaching along x direction, approaching along the y direction, and check whether all these or any other arbitrary direction, maybe y equal to x or some other arbitrary direction, and check whether what is the condition that needs to be satisfied for the derivative to exist. So, all right, let me start with the first one. F of z is equal to 1 by z. Um, Okay, so let's think about how to approach this problem. This, okay, this cycle I'll simply use Cauchy-Riemann as one example. Here I'll use that only. So since it's one divided by z, which is equal to 1 upon x plus iy. I'm writing it in the form of x comma y. So therefore f of x comma y simply gives me x minus, I'll do this 1 upon x plus iy. I'll multiply and divide by x minus iy just to normalize this. This gives me x divided by x square plus y square, which is the denominator. This denominator becomes x square plus y square minus of I into y upon x square plus y square. That's my f of x comma y. And in there, this is my u of x comma y. And this is my, with the negative sign, this is my v of x comma y with the negative sign, of course. So u is equal to x divided by x square plus y square. V is equal to minus y divided by x square plus y square. Now, I'll simply use the Cauchy-Riemann conditions here. This is the first method that I'm showing. For another part of the problem, another part, we'll use some other method. Okay. So, what is the Cauchy-Riemann condition? Do del u by del x is equal to del v by del y, del u by del y is equal to negative of del v by del x. So these are my Cauchy-Riemann conditions. So putting that here, using u and v of this form, what I get is del u by del x is minus x divided by x square plus y square, the whole square into 2x plus 1 divided by x square plus y square. This is my left hand side, and this is equal to uh, del v by del y. So again something similar, y divided by x square plus y square, the whole square, minus 1 divided by x square plus y square. So if you understand what I'm doing here, I am differentiating this using the chain rule, of course. But in my chain rule, the two functions are, so generally, what is your chain rule? Y is equal to f1 of x into f2 of x. So what you do is dy by dx is equal to df1 into f2 plus f1 into df2, right? So here I am taking f1 for the case of u. Suppose I'm talking about u. I'm taking f1 to be x and f2 to be 1 upon x square plus y square. This is my f2. So I'm simply using the multiplication rule only to do this differentiation. I can use the division rule, but multiplication rule also works. So this is straightforward. We've done this. So yeah, Sanjeev. So actually there is a lot of background noise. So maybe you can mute your mic. San Yeah, so there is some background noise from your part. So can you just mute your mic? Because it's a little bit disturbing. Yeah. Okay, thanks. Okay, so f1 is x and f2 is 1 upon x square plus y square. So this is how I'm using the multiplication rule to evaluate this derivative. So but nonetheless, you can see that there is no difficulty here. So this is what I get. And maybe I'll evaluate this one step lower. So doing this, what I get is minus 2x square divided by x square plus y square, the whole square, plus x square plus y square. I'm multiplying and divide by x square plus y square for the second term. So here the denominator becomes this the whole square, and this is equal to, oh, here I missed out 2y. My bad. So this is 2y square divided by x square plus y square, the whole square, minus same thing, multiply divided by x square plus y square divided by x square plus y square, the whole square. So again, this becomes equal to uh, y square minus x square. This numerator becomes y square minus x square divided by x square plus y square, the whole square. The right hand side becomes same thing, y square minus x square divided by x square plus y square, the whole square. So basically the left and right hand sides match. I should not have written equality from the beginning, but you can see that both the sides are same. So basically we get an equality between these two expressions. Similarly, I have to evaluate del u by del y as well. Uh, so del u by del y is simply minus x divided by x square plus y square, the whole square, into 2y. Del v by del x is equal to minus y divided by x square plus y square, the whole square, into 2x. Sorry, there is a plus sign here because raised to minus 1 becomes raised to minus 2. So there will be a plus sign here. The minus sign will go over. Right. So del u by del y also you can very clearly see is equal to negative of del v by del x. So this is also satisfied and this is also satisfied. Both the Cauchy-Riemann conditions are being satisfied. So we can claim that this is differentiable. The derivative exists. Here in general the derivative exists, except of course at the point 0 where we assume that z is not equal to 0. So except that point the derivative generally exists. So the question was whether it exists at least one point. So here definitely this derivative exists for more than one point. It exists for most points. So the first one is correct. Okay, let's see the second one. F of z is equal to x square plus I into y square. This is my f of z. So here also we can use those conditions, but we can use the Cauchy-Riemann conditions to do this as well. But let's try a more first principle method. So I'm just saying something del f by del z. So this is, I'm not claiming this is a derivative. I'm just checking uh, this variation of f with some complex number z, where z can be along say x axis or along the y axis. It can be anything of this. So I'm not saying that this del f by del z is the derivative. This is not necessarily equal to the derivative del f by del z. This is just some delta, something else. I'm checking whether it actually can take the form of a derivative. If both the approaches give me the same result, then it can be called a derivative. Okay, so I'm saying that this limit uh, del z tends to 0 where del z approaches along x axis. Okay, so what will this derivative be from first principles? This will simply be x plus del x, the whole square, plus iy square. Y won't change because my del z is approaching 0 from x direction. So del z is basically del x only. There is no del y component. Del z is equal to del x plus I into 0. Okay, so x plus del x the whole square plus iy square minus the original function which is x square minus iy square divided by del z which is del x. This gets cancelled. and here I get uh, 2x. Am I doing this correctly? 2x del x, yeah. What this gives me is just simply 2x. All right. Now let's see, let's make this del z approach from some other direction. So now my del z is going to be, say, 0 plus I del y. So in that case, del f by del z is equal to limit, again del z tends to 0, x square plus I y plus del y, the whole square, minus x square minus I y square divided by del y. So this goes away. I into y square, this also goes away. And what I'm left with is equal to I will be there, right? Oh, sorry, here also in the denominator also there is an I. So this I also gets cancelled. In the denominator also there is an I, of course. So the I gets cancelled. And what I'm left with is just simply 2y. The del y also gets cancelled from numerator and denominator. So what I'm left with is just 2y. There is 2x and there is 2y. So clearly the derivative is different uh, if I approach the point from x direction, if I approach the point from y direction, from the imaginary side. So clearly it is different. So in this case, but the question is whether the derivative exists for any one point. So what I want is this to be equal to this for any one point. So maybe for x equal to y equal to 0, or actually just x equal to y necessarily 0. For x equal to y, this works, right? At least till now we can see that if x is equal to y, along that line, all the points along that line, this works well. So that is one conclusion. Let's try one final variant and see whether this works out or not. So let's approach z from the direction 45 degrees to the x-axis. That would mean del x plus I del x. Okay, so let's see if we can get some conclusive thing here. X plus del x the whole square plus I y plus del x the whole square minus x square minus I y square divided by del x plus I del x. Okay, so what I'm left with is 2x del x plus 2I y del x divided by del x plus I del x. So this is the derivative when I'm approaching uh, from x equal to y, along x equal to y, right? When I'm approaching along x equal to y, this is the derivative. So in this case also, firstly there are two things here. One is the approach direction, which is x equal to y. So that's why del x and del y are equal. The condition that we derived previously is that my point is such that x equal to y. So my initial claim was that at x equal to y, the derivative might exist. At all points where x equal to y, the derivative might exist. So now let's check for this general scenario as well. So suppose I put in x equal to y here. Okay, so 2 into 2x del x plus 2I x del x divided by del x plus I del x. So I take 2x common outside, del x plus I del x divided by del x plus I del x. This gets cancelled and what I'm left with is just 2x. which is the same derivative that we got here. So what this tells me is that along all the points where x is equal to y, along that line for all the points, this derivative exists. Is that clear? If there is any confusion, please ask me a doubt. I can clear it right now. If you want to think, of course, you can take your time. Like think about it later. But if there is some doubt which you need to clear out immediately, please ask right now. Or if it's clear, please tell me it's clear. Guys, okay. Okay. If it's clear, then let's move ahead. So this was question number six. And for question number six, for the second option also, I'm marking a tick that because the question is that the derivative should exist at least one point. Here there are many points where the derivative exists. So yeah, the second one is also correct. Again, I said same thing you can do with Cauchy Riemann conditions as well. Maybe just I'll just give a quick try to that because it does not take much time. So f of z is this x square plus I y square. If I'm using Cauchy Riemann condition, del u by del x is equal to simply 2x, del v by del y is simply 2y. And I want these to be equal. So 2x is equal to 2y gives me x is equal to y as the condition. And the other part is just 0, 0 equals 0. The other Riemann condition, Cauchy Riemann condition. The second one is just 0 equal to 0. So that is always satisfied. This to satisfy the first condition as well, you will require x equal to y. So even Cauchy Riemann conditions tell you the same thing, of course. Okay, actually, I don't need this page. All right. So two questions I did. Remaining is your work, and I'll just move on further. So next is question number 7. Consider the function f of z is equal to z divided by z star the whole square. This is the function that we're taking, and they're asking which of the following statements are true. The limit of f of z as z approaches the origin along the real axis is the same as the limit of f of z as z approaches origin along the imaginary axis. Therefore, limit of z tends to 0, f of z exists. That's my first statement. So here again, the framing of the question is such that we'll have to check the statements. Okay, so first statement tells me that if I'm approaching z tend to 0 from the real axis and from the imaginary axis, I get the same value. So that the limit exists. Basically, that's what we want to check in the first part, in the first option. The second option tells me that limit f of z as z approaches origin along real axis is different from the limit when it approaches the origin from the imaginary axis. So here the second statement is claiming that these limits are not the same. They are different. Therefore, the limit does not exist. Third option is telling me about the approach angle to be 45 degrees. If you check the third and fourth option, they are talking about the approach angle to be 45 degrees. So basically, this question requires you to tackle two cases. We'll have to just try the approach, like we'll have to check the limit when z is approaching origin from real axis, imaginary axis, and 45-degree angle. So we'll try all these three and we'll see whether which of the statements is correct. Is the question clear? So guys, whoever don't have background noise and whoever can keep their mics unmuted, I would prefer if you guys keep your mics unmuted. You can just tell me whether you are understanding this or not, because otherwise this becomes a very the question you don't understand. Okay, so what the question is asking, if you read the first statement, so function is given and they want to check the statements. The first statement is limit of f of z as z approaches the origin along the real axis is the same as the limit of f of z as z approaches origin along the imaginary axis. So what we want to do is, we have some f of z and we want this z to approach to 0, basically to origin, from two different directions. Once I'm checking the limit when z is approaching 0 along the real axis, as in z is just simply x, there is no y there, and that x is tending to 0. Another limit is that z is equal to just iy, where y is tending to 0. And what I want to see is that in both these limits, the value of the function f of z comes out to be the same. That's the claim of the first statement. In both these situations, f of z should turn out to be the same. Then the first statement stands correct. And that also tells you that limit z tends to 0 exists, right? Because for any limit to exist, you need the value of the function to be same in whatever direction you approach. So that's the first statement. Did you understand the content of the first statement? What's possible or what's not possible? Whether it can be different or same. It can be different. That's what we will see. Not sure whether in this question. Like there do exist functions where the limit does not exist. We'll see whether it's the case for this one. Okay. All right. So let's try and check the first statement first. Okay. So I'm saying f of z tends to 0 is equal to, but along x direction. So my z is simply x plus I 0 and x is tending to 0. This is limit simply x tends to 0, x plus iy divided by x minus iy the whole square. I am claiming that y is already equal to 0. So this is just x square divided by x square is equal to 1. Right? So this limit is 1 when z is tending towards 0 towards the origin from x direction. This function, the value of this function is tending towards 1 when this is the particular direction I choose. Okay. Now I'll do the same thing along y direction. I'll take z is equal to 0 plus iy, where y tends to 0. Okay, so f of z becomes x plus iy divided by x minus iy the whole square, which is equal to x becomes 0, iy the whole square divided by minus iy the whole square. Even this comes out to be 1. So you can see that along both these directions, the limit is the same, right? So the first statement comes out to be true. Actually, limit z tends to 0 exists is an extension. Let's not claim that right now. But yeah, along both the directions, the limit is the same. Now let's try the third statement. The limit of f of z as z approaches origin along the real axis is what we wanted to check, which we have already checked, is different from the limit of f of z as z approaches origin along a direction 45 degrees between real and imaginary axis. What does this mean? This means that I'll take z is equal to x plus ix. So this is the 45-degree direction along which z is approaching origin. And here also x tends to 0. All right. So let's do this one. F of z is equal to x plus ix divided by x minus ix the whole square is equal to x square goes away. What I'm left with is 1 plus I divided by 1 minus I the whole square. Is this okay? which will give me um, 1 plus I multiplied. What does this give me? This is simply, I think, e raised to power I pi by 4 divided by square, right? 1 plus I is right. This is okay. Is this okay? 1 plus I am writing as e power I pi by 4 divided by 2. Sorry, into root 2. Root 2 into e power I pi by 4 is 1 plus I. So I'll say e power I pi by 4 is equal to cos pi by 4, which is 1 by root 2, plus I sin pi by 4. So I into 1 by root 2. This is e power I pi by 4. So root 2 into e power I pi by 4 is equal to 1 plus I. So that's what I'm using here, but the root 2 from numerator and denominator will cancel out. So that's why it's just e power I pi by 4 divided by e power minus I pi by 4, the whole square. So this is simply e power I pi, which is equal to minus 1. Do you see this now? Here the limit is different. Here the approach limit is giving me minus 1 along this direction. So what would you claim? So if I want the limit of the function to exist, it has to give me the same value along all directions. This function is giving me the same value along x direction and y direction, but not along x equal to y direction. So I cannot say that the limit exists, but I can still claim that some directions are appropriate. So basically the statement number 3 is the correct one. That limit of f of z as z approaches origin along real axis is different from the limit of ff as z approaches origin along 45-degree direction. Therefore, limit z tends to 0 does not exist. That's the correct statement. Is that okay? You are asking this exactly, right, Subhash? So this is clear to you? All right. So this is a possibility. This can happen. So complex functions behave in a much more weirder manner than the real functions that we see. So not a lot of statements that we think very normal or obvious in real function case, they need not be obvious or correct in the case of complex functions. So it's better to have a check. And this course actually provides that in a lot of good depth. So that's why it's good to follow along very well as sir is teaching. Okay. All right. So now question number 8. Okay. So this is something else. Okay. So this is the question. Consider the function. This function is slightly different. There is no, there is z star square in the numerator and z in the denominator. And the question is, which of the following statements is or are true? Multiple choice again. Limit z tends to 0, f of z exists. That's the first question. So now you know how to evaluate whether a certain limit exists or not. That we just saw. We tried to evaluate in 3 different directions. So something similar has to be done for the first statement to check whether the first statement is true or not. So I am not going to do the first statement. Second part is the function can be made continuous at the origin. How will you check whether this is correct or not? Please answer, Sanjeev, Subhash, anyone? Yeah, yeah, go ahead. No, come again. Tell me more clearly. So basically, yeah, I think what you are trying to say is correct. Um, so firstly, we'll check whether the limit exists or not. We'll check in all directions. Not all directions. Three are good enough. So you check along x, you check along y, you check along some random direction x equal to y. And if in all these three directions you see that the function approaches the same value, then you know that the limit exists. But at z equal to 0 exactly, because the numerator has z, so at exactly z equal to 0, the function is blowing up. But what the question is that can we make it continuous at the origin or not? So if the limit along all directions approaches the same value, then you can manually make it continuous by defining the value at z equal to 0 to be that value of the limit. Do you understand this statement? For example, I'll just, so even if you have not understood, I'll just give a small example. You know, like this is a very standard example, you must know this. Sin x upon x, is this a continuous function? So its limit, if you try to check its limit as x tends to 0, limit x tends to 0, sine of x divided by x is of course 1. But exactly at x equal to 0, this function is undefined, right? Because x goes to 0, then at exactly at x equal to 0, this blows up. It's 0 by 0 form, so it's undefined. Actually, it does not blow up. You don't know the value. But what the claim is that because the limit tends to 1 from all directions, then what you can do is for f of x is equal to sine x divided by x, define f of 0 is equal to 1. Since this limit is 1, you will define the limit f of the value f of 0 as 1. In by doing this, what you did is you made the function continuous. So similarly, the question being asked here is the function f of z, can it be made continuous at the origin? So all you have to do is check the limits. If the limits exist, then you can say that exactly that value you define it f of as f of 0, and you can make it continuous. So in the second statement can be answered by answering the first statement. Then the third statement is limit f of z as z approaches the origin along real axis is different from the limit as z approaches origin along an arbitrary angle theta to the real axis. So again, something very similar. There is a similar problem that sir has done in the lecture notes as well. So by approaching at some angle theta. So how will you do that? How do you show approaching at some angle theta? Your del z can be some epsilon e power I theta, where epsilon tends to 0. So the del z can be of this form. Till now you are taking the del z to be either say del x plus I into 0, or maybe 0 plus I into del y. Here in this case, del 0 will be of this form. Del z will be of this form for any arbitrary angle. So you can put this also in the equation and check whether the limit exists or not. Whether both these limits along the x-axis and along some arbitrary direction, do they come out to be the same or not? Okay, so you have to check all these statements. You have to check these three statements. And the final one, if you check the three statements, the final one you can answer. So this question I'm not directly telling you how to solve, but you know the approach. So you can try this one. Is that okay? If there is a doubt, please ask. Sanjeev, Subhash, some response? Is there a doubt? Okay, so I'll just assume that there is no doubt and I'll move forward. Okay. So the next one is ninth one is again consider the same function. It's the same one, right? Yes, it's the same function. So consider this function and which of the following statements are true? Which of the following statements? Only one statement is correct here. Okay. So Cauchy-Riemann conditions are satisfied at the origin, but the derivative does not exist. Uh, all right. So let's try and approach this problem. Okay. Hmm, we want to check at the origin. Okay. So let's do this. F of z is equal to z star square divided by z. Uh, Cauchy-Riemann condition for this function is del f by del z star is equal to del f by del z star is equal to 2z star divided by z. Z of course I'm taking as a constant and z star is which is the variable with which I'm differentiating. So I get 2z star by z and at origin does this become 0? Okay, wait, if z is not equal to 0, this is the function. If z equal to 0, then the function is 0. My bad. Um, so at the origin the function value is 0. Cauchy-Riemann conditions, in that case Cauchy-Riemann conditions are satisfied at the origin, right? Because at the origin the function value is just f of z is equal to 0 plus I0. So u is equal to 0 and v is equal to 0. So of course Cauchy-Riemann conditions are satisfied at origin exactly. But now they're asking the question that the derivative f prime of z does not exist at the origin. For that, we'll take the derivative from the right, as in we'll choose directions and take derivatives, either the real axis direction or the imaginary or both. So what we want to do is from first principles, we'll take derivative along the real axis. From first principles, we can take derivative along the imaginary axis. And we'll check whether these derivatives actually match the values. Basically, these derivatives should give the same value. That's when we can say the derivative exists, right? So let's check. Hmm. F of z plus del z, where initially del z is equal to del x plus I into 0. This is equal to, I'll have to write the x and y form of this function. It's right now in z star square divided by z form. So let's write it in that manner. X minus iy the whole square divided by x plus iy. So this is equal to x square plus y square minus 2ixy divided by x plus iy. This is my function, right? Do I need to normalize this? Let's do it nonetheless. X minus iy into x minus iy multiplied divided by both. So what I get here is x cube plus xy square minus 2ix square y. Yeah, yeah, sure. No problem. Leave. Sure, sure, sure. No, no worries, no worries. It's okay. Um, okay, so minus 2ixy um, minus I goes away. That gives me minus 1. Yes, so there is a minus sign remaining. So minus 2 x y square. This is the expression I'm left with, divided by x square plus y square. Okay, so slightly confused here. X y square. Oh, I hope this is correct. First was just simply x cube plus xy square minus 2y x square y. This is okay. Minus iy. So that is minus I x square y minus iy cube. And minus minus becomes plus, but I gives me minus again. 2x y square. Yeah, I think this is okay. Is equal to x cube. So xy square and xy square plus and minus. So minus xy square plus, okay, so two real terms and there are two imaginary terms, x square y. So minus 3i x square y minus I y cube. These are the two imaginary terms divided by x square plus y square. So this is my just my f of z actually. F of z. F of z is this. Now what I want to do is f of z plus delta z, where delta z is this delta x plus I into 0. So this is f of z plus delta z minus f of z divided by delta z. Limit delta z tends to 0. So what this becomes is uh, x plus del x the whole cube minus x plus del x into y square minus 3i x plus del x whole square y minus I y cube minus of x cube minus x y square minus 3i x square y minus I y cube. This is the whole expression. This whole divided by x plus ix the whole square plus, oh no, I made some mistake, of course. My bad. Let's do it like this. Sorry. Um, so this is the first term. This is my second term, right? This is my first term. This is my second term. So this is f of z plus delta z, this left hand term. And the denominator here is x plus delta x, the whole square, plus y square, minus this, where it's x square plus y square, simply. The denominator is just that. And the whole divided by delta x. So this already looks very tedious to solve, but yeah, let's do it. X cube plus 3 x square delta x minus xy square minus y square delta x minus 3i x square plus 2x delta x into y minus I y cube. This whole thing divided by x square plus 2x delta x plus y square into delta x. This denominator I'm taking here only, minus the second term I'm writing, x cube minus x y square minus 3i x square y minus I y cube divided by x square plus y square into delta x. So here clearly this term in the denominator is of no import. There is x square, there is y square. So this term is arbitrarily small and it does not really contribute anything. So I can just let this term go. So once I do that, the denominators become equal, of course. And I can simply cancel out things that I don't like, as in which I can cancel out. It's not that I don't like them. X cube gets cancelled, minus xy square also gets cancelled. 3i x square gets cancelled, I y cube gets cancelled. Of course, the uh, original terms get cancelled, right? This is now what I'm left with. And also there is a delta x term in the denominator, so that cancels uh, these numerator terms. Delta x gets cancelled from everywhere. And what I end up with is 3x square minus y square minus 6ix. 3x square minus y square minus 6i, 3 into 2 6ix, right? Y, there is y also outside, minus 6ixy. Okay, this divided by x square plus y square. And what I want to see is that whether f prime of z exists at the origin. That's the idea, to check whether that exists or not. So along the x direction, this is the expression that we end up with. And also I have to put x and y to be equal to 0 at the end, but clearly not in this case. Okay, let's check the other direction also first, then let's comment on this. F prime of z is equal to, now, okay, let's align here. Now delta z is equal to I delta y only. So in this new case, now I can simplify things a little bit or do this quicker. So x cube minus x into y square, which is y plus the approach direction is this, but I'm just taking y like that only, yes. So y plus delta y the whole square minus 3i x square y minus 3i x square into y plus delta y minus I y cube minus I into y plus delta y the whole cube divided by, we know that the denominator value of delta y does not matter. So I'll just put x square plus y square minus of into delta z, delta y. There should be an I here, I delta y. But the denominator will be there because it will simply be uh, the new z minus the old z. But in this case, the y value we are putting in, so this will be just delta y. So there will be an I in the denominator. Okay, yes, there should be an I in the denominator. Okay, and here it will be x cube minus xy square minus 3i x square y minus I y cube divided by x square plus y square into I delta y. Okay, so solving this, x cube goes away, xy square also will go away accordingly. What I'll be left with, I'll just write that only. Uh, 2y delta y minus 2xy delta y minus 3i x square delta y minus 3i y square delta y, and everything else will go away, and even these delta y's will get cancelled, so I'll not have these delta y's because there's a denominator delta y term, but I'll have an I in the denominator, I x square plus y square. Okay, so I really hope I'm doing this correctly. 3x square I can see, y square I can see, but there is 2xy, this is coming from here. All right, so okay, so what I see here is that the derivative that we evaluated in this case here and the derivative that we evaluated here, these both seem different, right? So it would seem to me that f prime of z, as z tends to 0, is not, the derivative does not exist because the derivative values are clearly different as I like according to the direction where I'm approaching. So even though I can see that Cauchy-Riemann conditions are being satisfied because the function is a constant at origin. So u and v both are 0. I'll just take the derivative and the Cauchy-Riemann conditions can be satisfied trivially. But f prime of z in two different directions is clearly giving me two different values. The value here that I'm getting, if I put some small x and y value, the value that I get here, if I put some small x or y value, it's not exactly 0. It is some uh, small value. So if I put those values here, I'll get two different results. So that's why f prime of z does not exist. That would be the conclusion. But nonetheless, you should check this for yourself and see whether this happens or not for you. All right. Now the last one, last question. Okay, I'm just copying this. Okay, just give me a moment. I'm sorry. Um, so this is your question. Let's put it up like this. Yes. So suppose we consider a function um, of a complex variable z as a function of two real variables x and y. That's what we generally do. Which of the following statements is a compact way of stating the Cauchy-Riemann conditions? The statements are given here. So, and there is only one correct answer clearly. So what they are saying is that complex function of a complex variable z equal to x plus iy. So f is basically a function of z and it's a function of x plus iy. So we want to restate Cauchy-Riemann conditions in this form. Okay, so let's put it up like this. An easier way to do this would be just this. If I say that f is just simply u of x plus iy, x comma y plus I v of x comma y. So let's check the first statement. Del f by del x is equal to del u by del x plus I del v by del x. Del f by del y on the other hand is equal to del u by del y plus I del v by del y, right? So put it up together. Del f by del x plus I del f by del y is simply equal to del u by del x plus I del v by del x plus I del u by del y. I into I is minus del v by del y. And the statement is that this is equal to 0. So what we want to see is whether this statement gives us the Cauchy-Riemann conditions or not. Or basically it's just a restatement of Cauchy-Riemann conditions is what we want to check. So simply you know that because right hand side is 0 and u is a completely real part of f of z and v is the completely imaginary part of f of z. We have separated these two parts. So simply equate real part and imaginary part both equal to 0. That's your uh, that's all that you need to do. So the real part is del u by del x is equal to del v by del y. That is the first condition that comes out. The second condition that comes out is del v by del x is equal to minus del u by del y. And these are exactly your Cauchy-Riemann conditions. So clearly this is a compact way of writing Cauchy-Riemann conditions. You can check the other options also, whether they give you something of that sort, something like Cauchy-Riemann condition. If not, then those options can be eliminated. So I'm not solving the whole question, as I said. I just solved the first statement. That came out to be correct. So you do the rest, check whether others are not, because clearly this is only single choice question. So I already gave you the answer here, but nonetheless, you should check the other statements so that you have a practice of solving these kinds of problems. So, yep, that's the 10 questions. Now, having done the assignment part, are there any questions in the lectures? The lectures that sir has taken in week 1 lectures, are there any doubts in those lectures? Are there any other doubts that you have in general about complex functions or complex numbers? Anything that you have in mind, we can discuss that. Is there anything that you want to discuss? Sanjeev, Nagananthini, anyone? Okay, so no, all right. Uh, so anyway, even if you have some doubts, there are two ways to get your doubts solved. One is that you can ask me in the live sessions, or you can put it up in the forum as well. You can write the doubts in the forum, and either me or a professor, whoever sees those doubts, they will reach out, like they will answer those questions. You can post it up on the forum as well. But because there are live sessions happening, if I am able to clear those doubts, it would be easier for you as well. That I right here can clear out doubts in a live session. So take advantage of these sessions because you are anyway attending them, right? Yeah, go ahead. I am anyway going to put up these recordings, and you might have those. You'll be shared some Google Sheet or something where I'll be putting up this recording as well and the notes that I've written while doing this. Yeah, so you'll have access to it basically. All right. Okay. Anything else? All right. Okay. So that's the end of the session. Thank you for joining. Bye.